Welcome. My name is Amon Abraham.
Hi everyone, I'm Jason Garcia.
And I'm Joshua Curtis Gafor, and we are Renewable Minds.
Just for a brief overview on the Lost Hills project, this is a few statistics that we had. The Lost Hills oil field is a large oil field in the Lost Hills region, north of the town of Lost Hills in the West Kern County, California, in the United States.
The solar project, which was completed in April 2020, brought more sustainable resources to the Lost Hills oil field, which was discovered in 1910 and has produced more than 460 million barrels of oil over the past 40 years. The project is among the largest solar electric systems in California's net energy metering program.
It is estimated that the project has 19,800 metric tons of low carbon fuel standard credits being generated as a result. Due to the fact that this is a solar panel region, some of the energy can also be stored in batteries as well. This allows for an additional 2,700 metric tons of LCFS credits being generated as a result. And by totaling up the solar energy consumed and stored and converting it to kilowatt hours, we tabulated a value of about 44,107,000 kilowatt hours in total.
And we also found the statistics for the impact of this solar project. Over the PPA's 20-year potential term, the project is expected to produce more than 1.4 billion kilowatt hours of solar energy.
The project also meets 80% of the power needs for the Lost Hills oil field.
The project is also estimated to generate approximately 38,700 megawatt hours of solar electricity per year, which is enough to displace power currently provided by Pacific Gas and Electricity.
And we estimated the emissions reduction from the solar electricity directly supplied to the oil field is 19,800 metric tons of CO2e per year.
So now we will go over what we thought were the greatest contributors to Scope 1 and Scope 2 emissions before the project. So for Scope 1, our biggest contributors were the barrels of oils produced. So there were 9.7 million barrels produced in 2018. This led to the calculation of 2,286,290 metric tons of CO2e.
Another contributor is a Scope 1 emission, and it's the operation of the Lost Hills oil field. We estimated it to be 28,000 metric tons of CO2e per year to operate the oil rigs.
And moving on to Scope 2 emissions, we determined that reduction was a key part of Scope 2. We calculated that emission reduction due to solar electricity was 19,800 metric tons. And in addition, imported electricity and steam made up a big part of Scope 2 emissions, and taking Chevron's annually report and proportionating it to how Lost Hills are, we tabulated 38,574.38 metric tons of CO2 equivalent per year.
So now we will go over some alternative solutions. So I'll be going over wind turbines. Background, an average wind turbine can produce 6 million kilowatt hour. We estimated the cost to produce 44 million kilowatt hour would be 30 million because you'd be building 8 wind turbines. The approximate timeline was about 3 to 5 months, and emissions would be essentially zero, but there'd be emissions from the installation process.
The second solution was building off of a previous Chevron project, which was using biofuel generation. So since this project takes place in California, the idea is to use a biomass reactor to provide electricity and provide heat for steam production, and potential sources could be maize, algae, sugarcane, and waste. The cost could be about 19 million to 21 million per year to run the plant, but it would also reduce emissions by about 64%.
And the solution 3 is just improving the battery. We found that the problem with the energy is the storage of it as well. The existing solar panel batteries have a degradation of 2.5%, which reduces the amount of power that we could store. This becomes increasingly more prevalent if you consider that we're receiving a
Fine.
surplus of.
Please wrap up your last thought.
Okay. If you consider we're receiving a surplus of energy during the summer of each year, our solution to this is a battery with lower degradation rate. Sorry. And yeah, that's
Great. Thank you. This begins the 5-minute Q&A with the judges.
Okay, I'm Barbara Berger. Great job. I also know all of you are in your first year at MIT, so well done to kind of focus on this just a couple of months into your schooling. I wanted you to go through your scope 1 again. You had 2 categories. One was the production and one was the operation. And my understanding of scope 1 is those are that it is the operation, it is making your product that is scope 1. So can you tell me the difference between your first 2?
Yeah, so I'll go ahead. So essentially what we thought operations were like the process used to produce the oil.
Yep.
So like we separated between using machinery and how much CO2 that produces, and we also separated like the oil itself and how much CO2 that produces.
When it's used?
Yeah.
Was your idea? Okay, I got it. All right, thank you.
Again, thank you very much. It's a great presentation. And I know you ran out of time, so I just want to give you the question to answer. For the proposed solutions, what steps that you see that can increase the impact significantly? I don't know whether you had it in your slides at the end. What do you see as a step change that may be able to do? I believe you had access to the MAC curves, that's the abatement curves, and the impact for this plant. So, you know, what is the biggest impact you see from the solutions that you propose? I'm not sure whether you have it in your slides down the road.
yeah. You want to go, Jason? I was gonna in slide or solution number 3 when talking about the battery. I didn't have enough time to talk about it, but for this proposed solution, it would just be increasing or decreasing the degradation rate, and basically the plan with that is you would save up 8 to 10% of your total energy within like the 20-year plan that you guys have. And we did a little bit of research, and it's hard to scope what batteries are already in use. But just based on a little bit of research, we saw some articles on this technology called sand batteries, where sand basically keeps in the heat capacity that could also simple altering of that technology, you guys could save a lot more energy within that plan. Did I cut out?
No, you're good. Thank you.
Okay.
Okay.
With your solution 1 with the wind turbines and your solution 3, is this kind of an either or do you plan to do both of these things? Because as I understand it, the wind turbines would be intended to produce power more consistently. Then the batteries seem to maybe be approaching the same problem. Could you kind of speak to that a little bit?
Yeah, so I think I'll speak to it. Essentially, what I was thinking of was that wind turbines would replace the current system that we have. So I try to make a model where wind turbines would produce the same amount of energy, which was 44,107,000 kilowatt hours, and I would see how much that would cost. And then I noted that the emissions would be around 0, so that's essentially optimal. Yeah, it's pretty much the model I took.
And then regarding batteries, they could also be applied in tandem. This is referring simply just to storage of energy. So using wind power to generate energy as well as solar power to create energy and also store it as well to send it to the grid is an optimal solution.
Okay. I think that might be all for questions then.
All right, awesome. In that case, you guys have finished just in time. Thank you very much for your presentation. You may leave the meeting now and we will let in the next team. And good luck.